Thank you, Dave, first of all, and Ned and Nico for inviting me here. I'm really honored to be speaking here. And the only problem I have is that maybe, Melanie, you created a lot of expectation on this perturbation and complexity. And now I would like to just leave, to be honest. But okay. So, mine is going to be a neurophysiological talk. I'll try, I mean, not hardcore in the end and not, I hope it's not going to be a tour de force. I'll try to deliver basic concepts, and after all, the technique we use, the neurophysiological approach we use is really coarse and brutal. We bang on the brain with a magnetic, probe, and then we get the echo. So there's nothing really fancy or, or difficult in this terms, or not many technicalities. So I'll go through this series of experiments we performed in the last 10 years now. We started in 2003, 2004 actually, and where we used a combination of TMS, transcranial magnetic stimulation, and electroencephalography to probe the brain in different conditions where consciousness is present, gone, and recovered, such as non-REM sleep, dreaming, anesthesia with different anesthetics like propofol, midazolam, xenon, ketamine also, which is very interesting. And then finally we moved to the patient bedside, and we probed the brain of patients emerging from coma towards different clinical states. And I want to say from the start that this is a teamwork. I mean, involving the University of Milan, but especially the Coma Science Group in Liège, Stephen, Melanie, and Wisconsin, where Giulio is, and many other people. So we acted as one lab, and this has been, for me, a beautiful experience, still is, actually. So, but when we started, we didn't have any diagnostic problems or patient in mind. Actually, we really wanted to test a basic theoretical prediction that is that consciousness has to do, as Melanie laid out, with a specific kind of complexity. And just let me summarize. I'm sorry if I repeat something that Melanie already said in much better ways, but I just want to say, to lay out the rationale of our practical approach, a couple of points. One is consciousness can be present but disconnected on the input and output side. So when we dream, we've said it already, we are disconnected. We perceive nothing of the environment. They can tape our eyes open, put us in front of a movie, we dream of something else. At the same time, we are paralyzed because of physiological mechanism. And an even more extreme case is ketamine, which has been mentioned. You can be conscious, maybe you have hallucinations, intense, vivid consciousness. We collected incredible stories from our subjects, and you are disconnected to the point you can have surgery. And then this can happen also in patients, of course, to be disconnected on the input and output side. So this is one principle. And then the point is we need to find a measure that is directly derived from the brain, that doesn't rely on the ability of the subject to comprehend, to respond to stimuli, to get information from the outside, and doesn't rely to his behavioral abilities or motor abilities. The problem is, as Melanie laid out, that we have good candidates, and there are many good measures, and probably by combining them, we will get far. But we don't have, a metric that functions well at the single subject level across different conditions where consciousness is lost and recovered. Epilepsy is one case where actually activity, so metabolism goes along with consciousness, and it's a very good indicator, but there are cases where it increases and consciousness is gone. The same is true for synchrony. Neurosynchrony is a good candidate. When we're conscious of something, we perceive a phase. Synchrony increases, but synchrony increases even more in propofol anesthesia when you're gone, and seizures. So, finding the metric, and that's where theory can help, and I will lay out the theory in a brutal way. I mean, I'm glad Tononi is not here because, so, but Melanie did it already for me. So it starts from phenomenology, and that's the main axiom, and it comes information in these terms. It's not because the scene is rich and complex, but because it rules out countless possible other options. It means the brain has the machinery to enter all these states, so it's very differentiated inside, and at the same time it cannot be split. When the brain enters one particular state out of many, it does it as a single piece. So you cannot see the base and the two faces at the same time. And but coming to neurophysiology, back to neurophysiology, that suggests that it's not so much activity level, synchrony, or responses to input that we need to measure, but it's this balance between unity and diversity, or function integration and function differentiation in the brain. I'll call it henceforth complexity because it's simpler. And to give an idea what it means, because it's a very difficult balance. If you try to implement it in physical system, it is really, really difficult. Give an example. This is a system that is surely differentiated, different set of elements, they have different set of connections, but it's modular, clearly modular. So this is not integrated. Other end of the spectrum, this is a system that is fully interconnected, surely integrated, but not many degrees of freedom. So there's no information in here. To achieve this balance on a simple system of 8 elements, or to optimize the balance between integration and information, a computer takes hours. So it is not easy to get. And this is the kind of balance we need to assess. And there is a measure for this, which is phi, but it cannot be applied for the moment to, not even remotely, to real brains. So we came up with a brutal and coarse approximation. And the approximation goes like this. It is not enough to observe the brain, because you need to explore causal relationship, you need to explore integration by causal perspective, so you need to hit the brain somehow, and then you need to record the response to the brain. And the rationale is that if a system is not integrated, the response is going to be local. If the system is maybe integrated, connected, but is homogeneous, lacks differentiation, the response is going to be global, but stereotypical, simple, all or none. Only if the system is balanced, you're going to have an interesting spatiotemporal pattern that is both global and differentiated, difficult to describe in one word. So this is the kind of complexity we want to measure, and we have to do this in real brains. So that's why we came up with this kind of complicated technique that combines transcranial magnetic stimulation and electroencephalography. This is an example of the experimental setup. So you see here subject sitting on a chair. This is the stimulator, so it generates for a fraction of a millisecond powerful magnetic field, about 2 Tesla, which in turn activate the patch of cortex. So axons are firing, and then there's a navigation system in order for you to know where you're stimulating, how strong, and to be reproducible. But what's most important is this EEG system that is compatible with TMS. So you can really record the response of a cortical perturbation directly in the space of a few milliseconds with a decent spatial resolution. So we have about 60 electrodes. So the kind of data I will show from now on this kind of cortical evoked potential. So it's causality within the brain. We bypass input and output. And this is the kind of measure that, coarsely can approximate what we said before. Then we have this measure, and we want to test it wrong or right in different conditions where consciousness is there, presumably there, or not. So one is sleep, natural. Another one is anesthesia, and as I said, we tried different anesthetic, and finally, the patient. So I will go through this data quickly. Sleep was the first experiment. So normally what happens is that we perturb the brain in wakefulness, we collect good evoked potential, meaning we do many trials, then we see what's the response. We have a solid, statistically solid response, and then the subject falls asleep, and we keep stimulating, and we compare. So this is a comparison between somebody who's awake and somebody who's asleep. This is wakefulness. So we perturb here, and then we record from all these sensors, and this is what we get in terms of wave shape. This is an electrical echo of the brain to this knocking. And what you see is that many electrodes are responding, and each electrode is responding in a different way. So already, in a qualitative terms, you can say it's widespread and differentiated. So maybe it's better in this way. So in this case, we are now looking at the same data, but this is source modeling. So we look at the currents generated. We estimate the current generated in the brain by the perturbation. There's an initial activation under the stimulator, and then activity travels in an interesting way, which is global and differentiated in the cortex. And it lasts for about 300 milliseconds. So this is the typical pattern of wakefulness. And you can summarize this in a snapshot by just painting on the cortex areas that were significantly active, latency is color-coded. So it's long range, long-lasting activation, complex activity moving from one place to another. Now, subject falls asleep, N3, if you wake him up, it tells you a blank report. So you ask him what was going on in your mind, and he said nothing. So best of your knowledge, he was unconscious. So we cannot do better. And this is the kind of response we have. So it's a big wave, positive, negative. It's very different. The brain is active and reactive. The response is even bigger than in wakefulness, but the pattern of spatiotemporal activation is completely different. So what happens here is that the stimulator triggers strong activity, only the module that it's been directly perturbed, and this activity does not propagate. So this sounds like a breakdown of integration. And you can, and it's also shorter in this case, the response. And you can, plot it like this. Okay, so far, this looks in qualitative terms like this, and in this case, like this. It's modular. But one can ask, okay, thank you. We know that neurons in non-REM sleep are hyperpolarized, and then maybe they're lazy. You have to hit them harder. And this is a good question. So we actually perturb the brain with a very strong pulse, about 160 motor threads. So it's something really strong. It's like a hammer. And what happens, the best result we can get, we don't overcome this breakdown of integration. Actually, we have a big response, which spreads like an oil spot. So, I mean, yes, maybe the activity propagates, but in a way that is not interesting anymore. It's like tossing a stone in a pond. It's an oil spot propagation that it's typical of an homogeneous system. Again, we are speaking in qualitative terms. So this is good, so far so good. And then we tried anesthetics, a whole different way to lose consciousness. And what happens, long story short, is just the kind of response we find. It's very similar, actually almost identical to the one we find in sleep, no matter what's the anesthetic. So this is midazolam, this is propofol, this is xenon. Maybe propofol is more like on the loss of integration side. Xenon is more on the loss of differentiation side, but in all cases, complexity is gone. And this is very reproducible. Then we ask one more question, which might be relevant for patients. What happens in REM sleep when you're dreaming? Still, you're disconnected. And at the moment you perform the measurement, you don't know what's going on. I mean, from behavior. This is a subject who's awake, non-REM sleep, simple response, and then REM complex response. You wake up the subject and you get a story of 350 words, more or less, in this case. So, it's a delayed report, so the subject was conscious, but at the moment when you perform the measurement, you don't know, but you have complexity. Now, this is promising, and you can move to patients at this point. This is what we did in Liège. Also, the anesthesia actually was done in Liège, propofol, xenon, and ketamine. And this is what happens. So basically, patients, vegetative state patient, provided you hit the brain guided by MRI, healthy portions of the brain. Of course, if you hit a lesion, you get nothing, but that's natural. Provided you hit healthy portions of the cortex, you get a response that is sleep-like, except for post-anoxic patients like this one, where you have nothing because there's, most of the neurons are dead there. And this is very reproducible. No, these are the first 5 subjects we published, but we have many. And it's always like this. It's a big wave, which is either local or simple. Locked-in patients, complex response, just as in wakefulness. And what was interesting and promising to us is the MCS condition, minimally conscious patients. By this electrophysiological point of view, they're very different from vegetative patients. And it's eyeball. When you perform the experiment and you're there, you see that the response is different. You don't need statistics. This is what you see, the average that you see when you are performing the measurement. And this is really a crucial comparison. So, summing up, for now, we have assessed different conditions. When consciousness is absent, response is either local like this or global but stereotypical. And when consciousness is present, based on what the subject tells you right there, or based on a delayed report, or because after a careful clinical evaluation, the response is complex. It's just like this. Now, all this is interesting. Also, it's interesting that you can be sensitive in these cases, but it's all qualitative, and you need to come up with some quantification of this complexity in a way that is, meaningfully in also theoretical terms. So the idea is to basically hit the brain, get the response, the deterministic response, and zip it, compress it to assess its information content. So the principle is, okay, you do TMS, then you get deterministic activation. These are activations that are causally due to the perturbation. There's no noise in here. Come up with a matrix because you binarize the signal, 1 and 0's matrix. And at this point, you treat this as just an image that you want to compress and send to an email. And you come up with this. So you compress it using Lempelet-Zip complexity, which is the zipping algorithm, and then you come up with this PCI, perturbation complexity. Principle is that if the system is not integrated, the response is going to be small and easy to compress. If the system is integrated but homogeneous, the response is going to be global, big, it's a big file, but it's redundant. You can compress it using just a little bit of information, and only if the system is balanced, it is both integrated and differentiated, then you will have hard time compressing it. So this is the idea, and this is the metric we come up. So first we tested in healthy subject to make sure it's stable, provided you're conscious, no matter how you stimulate the brain, provided you stimulate above threshold, and we are forced to stimulate for technical reason I don't go into, but like a midline strip, frontoparietal strip. What happens is that you have these levels of complexity that are stable, reproducible across subject. Complexity changes only when subjects are sleeping in non-REM, anesthetized with midazolam, anesthetized with xenon or propofol, and you come up with this nice distribution. These are two separate distributions. This is already a good result because they're very far and there's no overlap. So this is a good scale of reference because you know where these patients are, where these subjects are. They tell you, either when they're awake or when they wake up. And then another property, and I agree with Nico that, okay, this measure is graded because in anesthesia level 3, it's intermediate levels, but I don't think it will tell you much about the actual quality or quantity. I mean, it's good that it's graded, but it's coarse. It's still very coarse. And it's intermediate in stage 1 and so on. But, it's just to show that it's not, of course, all or none, because I don't expect complexity and consciousness to be all or none. Now, we have this distribution, and this is in known condition. We know where the subjects are, we know where they are. Now, we take patients where we know where they are, because locked-in patients, severe brain injury patients, and minimally conscious patients, they show behavioral consciousness, and they are all here. So red is locked in, these are big brain lesions, and these are minimally conscious patients. So they are all above this unconsciousness distribution, which is good, so we don't miss a single subject, right? Be it dreaming, awake, or MCS. So this is, sensitivity is 1 in this condition where we know where they are. Okay, now we go to the unknown, because as we said, we have problems here with vegetative state patients. So these are patients who've been assessed repeatedly with the common recovery scale. Most of them are here in this distribution. But of course, we find also patients there. And now, what do we say? So this is the problem, as usual. And, but we have, high sensitivity and high specificity, which helps in a way. So confusion matrix in this crucial condition tells you that sensitivity is 1, because we don't miss a conscious patient, and specificity is lower because we have these 4 patients. So now, are these false positives? How do we go? And I remind you, we assume that we cannot access the brain to sensory input and motor output. This is our initial assumption and our goal. So what we can do, and the best thing we can do actually for now, is to perform an experiment with ketamine. Ketamine is a good model of disconnection because subjects in ketamine, they look like vegetative. Their eyes is open, they're fully disconnected, and still they are conscious. And they wouldn't be able to play tennis in the scanner, they wouldn't be able to watch a movie, to do nothing. They're completely in their own world, but they are conscious. And what happens is ketamine complexity is high. So now this, in a way, is the only thing we can say about these patients. That's all. So PCI can be high in somebody who's completely disconnected but conscious. That's what we can say in diagnostic terms. I'm done with this thing. I just want to say that, this result of specificity and sensitivity was not, we didn't look for a metric in patients. We started, with sleep and trying to approximate a theory. So to me, this is the striking part of this story. We were not interested in that. We became interested later in this issue. If I have 5 more minutes, do I? Dave, sorry, Dave, do I have 5 more minutes? Or? Yeah. Okay, because I just want to tap into the mechanism of loss and recovery of complexity, because I think this is important, and Nico already went there, and I think this is a very important field, although I realize that here it might not be so relevant, but I think it is relevant also theoretically and in principle, because once you have a measure of complexity that is relevant for consciousness, complexity has features like it's very easy to destroy. It's very easy to kill. So, you know, it is interesting to go and look as a physiologist, as a neurophysiologist, to what can be responsible for this collapse and maybe recovery of complexity. So, for instance, this patient is one of the longitudinal patients we studied in Liège, and patient is in a coma, opens her eyes, she's vegetative. You see this simple response, typical of sleep, anesthesia, vegetative state. Then she's still VS, but in the meantime, she was tracking a few days before. Then she goes back into the vegetative state. But you see, something has changed in the brain, and then she recovers and she's able to communicate. But here, something changed. So it is important to understand what happens there. And I don't think it's a structural change necessarily. So it's something functional in the circuits. And so I take sleep again as a model because I think it's still a good model. So we have to explain this. How come a complex response collapses in this slow wave that can be either local or global, but it's always a slow wave? What is this slow wave? So one possibility is that the mechanism that is responsible for the complexity, for the collapse of complexity, is the same mechanism that is responsible for the occurrence of spontaneous sleep slow waves. That is, I don't want to be too technical, but I think the concept can be, you know, delivered. It is bistability in thalamocortical circuits. When we fall asleep, what happens is that neurons start alternating between, so they're active, and then it's every once in a while, sometimes every second or less, every 2, 3, 4, 5 seconds, they drop into a down state. They're silent. And all the brain, it's a very widespread and synchronous phenomenon. And this is reflected in slow waves. This is due basically to activity-dependent potassium currents. What's that? So when we fall asleep, the brainstem is firing less, there is less cholinergic, noradrenergic pressure, and these channels are becoming more potent, stronger. And these currents are made in a way that the more the neurons try to be active, the more they open, potassium is positive, charge, and flows out of the neurons, and the neurons are basically becoming more negative, and they become silent. So the more they try to become active, the more they tend to become silent. This is bistability, and it's clearly a killer for complexity, if you want, because there are no ways in between. It's all either hyperactive or silent. So this is the idea, that this is the killer. So how do we demonstrate this? It's not easy. So first of all, there are simulations, computer simulation. This is a simulation by Stephen Esser, who simulated TMS on a thalamocortical system. It's a very detailed model, who's awake. So there is this cortical perturbation, activity propagates. So causal interactions are there. There is some degree of differentiation. So it's an interesting pattern for a simulation. Now, you open potassium channels. That's the only thing you do. You change a detail at the level of single neurons. It's a miserable channel for an ion. And this is what happens to the whole network. You perturb it, it gets activated, and then silent. And then after, activity resumes in a way that is stochastic with respect to the initial input. Causality, which is crucial for building up this kind of complexity, is lost. And so if this is the case, first of all, we said we need to be able to trigger big slow waves with TMS. And actually, this is possible. You just hit hard, and you get these slow waves that are just the same waves as sleep in terms of amplitude. But you don't know if this is a silent period. So the only way to understand that is to go intracranially. So we exploited perturbation and recordings in implanted patients for epilepsy surgery evaluation. And this is what happens. So first of all, we replicate the TMS EEG result, but this is intracranial perturbation and recording, wakefulness, complex wave, sleep, up, down. And what's most important is that you can characterize what happens or infer on neuronal activity. So, forgive me, this is a bit complicated, but I think it's very evident when you see the full picture. In wakefulness, you have an increase in power, fine. So there is no suppression of activity, because you would see the suppression of activity as a suppression of high frequency power above 20 Hertz. When the neurons are silent, you have no power above 20 Hertz. This we know from animal experiments. So you don't have this here, and you have this curve here is showing phase locking, the memory of the initial input. So the deterministic effect of the input. So this is causality. In neurophysiological terms, this is pure causality. So you have an input, and the system keeps track of the input causally for 600 milliseconds. Sleep, this is what happens. You have a strong suppression, you have big wave, strong suppression of high frequencies, meaning a hyperpolarization of the neuron. The neuron are shutting down, and then after they forget, because activity resumes stochastically, and they don't know what happened. So each target, and this is crucial for effective connectivity, causality, and whatever builds up complexity, they forget, it's gone. Causality is lost completely. It becomes a stochastic process after about 150, 200 milliseconds. So this, we think, it's a key thing happening in non-REM sleep, and it's due to a very simple thing, opening potassium channels. Then we asked, can we see something similar in vegetative state patients? And we only have TMS-EG. And in sleep, TMS-EG, you don't see that because of signal-to-noise ratio. This is a healthy subject, and this is a vegetative state patient. So you have this silent period. You have that. We don't know where it is due to potassium currents, too much inhibition, whatever the mechanism or this facilitation, we don't know, but it's there, and it's very reproducible. And there are many mechanisms, actually, that can bring to bistability. You can increase potassium channel because you have a brainstem problem. You can have this facilitation because of basal ganglia not exciting the cortex. You can have this connection is a typical model of bistability, the SLAB that Nico mentioned before. So you can have critical levels of disconnection, like axonal injury. On top of that, you have a share of functional disconnection due to bistability. So this is an interesting hypothesis, and even more so because patients who recover, they showed this, decrease of bistability and increase of causality. But in MCS patients, you still have it, so you can improve that potentially. So this would be one idea. And the other interesting thing is that we know, because plenty of people for 20 years, they've been working on this slow oscillation and bistability in animals because it was interesting for sleep. We know the pharmacology, we know the mechanism, synaptic conductance, everything. So this could be potentially a good target for therapy, especially considering that this is on top of structural lesions. And maybe it's reversible, and this is reversible in sleep when you wake up on anesthesia. And also, I want to remind that there are few patients who have metabolic activation in one hemisphere, potentially enough to be conscious, and if you hit them on the destroyed hemisphere, you see nothing, but here they're stuck in a low complexity state, bistable. So I think this is worth, pursuing. And this is a benefit of having a theory and a measure, because it gives you also physiological insight, I think. So to summarize, this is a theory-driven approach. It is independent of sensory input and motor output by nature, because we use TMS-EG. And we tested it in different conditions. We miss epilepsy, but we'll try, maybe, if possible. And then, you have the benefit of this high sensitivity and high specificity, even if we didn't look for it. And it provides some mechanistic insight. So, thank you very much.